Our next speaker is Steve Belch.
Thanks very much. I'm going to talk about conductance estimates, which is something that we do very poorly. I'll focus on HTEM systems, which are helicopter time to main EM. And I classify high conductance targets as superconductors because they are so conductive that we can't see them, we can't estimate their conductance easily with our band-limited systems. So the problem is that a lot of sulfide-rich mineral deposits can be highly conductive, and most HTEM methods are predominantly off-time, and off-time systems produce a low amplitude response in the late time for such targets. This is something that we know, and we've known for over 60 years. One solution is to measure during the transmitter on time, where the high conductance targets have a high amplitude relative to the off time. And this is not so easy with airborne systems because the geometry of the transmitter platform changes even slightly and creates large changes in the primary field. But we can express the off time and the on time as a ratio if we have a full waveform system, which we all have. And the method that I've developed is waveform independent and is not affected by the primary field. I call it the transient phase method because it is analogous to the phase in the frequency domain. Frequency domain phase is the ratio of the quadrature to in-phase response, and transient phase is just the ratio of the off time to the on time. These are three very simple equations. The first one is if you integrate the primary field during the transmitter on time, it is zero. Of course, we can't integrate the primary field because we can't separate the secondary field and the primary field during the transmitter on time. However, if we also integrate the secondary field during the transmitter on time, it will equal a -1 times the secondary field. So if you consider the total field to be a sum of the primary field and the secondary field during the transmitter on time, if you integrate that, you get a -1 times the secondary field and no primary field. That's for, say, n samples in the on time. If your half cycle is capital N, you just integrate the off time from n+1 to capital N, and that is the off time secondary field. So the transient phase is just the inverse tan of the total off time or the total on time, where the off time is equivalent to quadrature phase and the on time is equivalent to the in phase. I know you're going to ask me why I'm bothering doing this, so I'm going to tell you in a second. So we set up some calibration coils where we place the coils on the ground. They're of increasing conductance. The highest one is around 10.8 milliseconds. The lowest is I think 20 microseconds. And here we have five such coils. On the left is the off time. On the right is the on time. That is a culvert, which we detected. And this is an older culvert and a much older culvert. So ignore the culverts and just look at the peaks. You can see that as you go from low conductance to high conductance in the off time, there's a drop in the overall amplitude. And from the off time, as you increase in conductance, it'll reach a peak, and then it has a decreasing amplitude. But you can see the late on time has a very strong response. And this is done at 150 hertz. So if we integrate that, you can see moving from right to left, the off time dominates, and then the on time dominates. I've left the on time as a negative. And so for 30 hertz as an example, we can look at the actual time constant, which is on the left. We can look at the kind of conventionally calculated time constant from the late time channels in the center, and then we can look at the transient phase. And in the first instance, at 0.25 milliseconds, you see it's over 45 degrees, which shouldn't be. Everything should be from 45 degrees down to 0 degrees. But for the late time at 30 hertz, we're only at 33 degrees, so we have a lot of conductance discrimination to go. But it's more useful if I show you a real field example. This was flown earlier this year. The upper profiles are off time in nanoteslas per second, and the lower profiles are on time in nanoteslas per second. You can see that the on time peak is almost twice the amplitude as the off time peak. And so if we integrate the off time, we get a value of 459. This is at 90 hertz. And if we integrate the on time, we get a value of over 1300. The inverse tan of that is 19.1 degrees. So you can tell the client, congratulations, you have a conductor with a 19.1 degree transient phase. So what does that mean? Well, if you have a conductor that is decaying where the time constant is much shorter than the transmitter on time, you will have an equal amount of response in the on time and the off time. So you'll never exceed 45 degrees of the transient phase. Here we measured 19.1 degrees transient phase. And when you calculate the time domain, the tau using the normal dB by dt, you get just under 700 microseconds. If you integrate that to get an off-time only B field, you get 1.2 milliseconds. But if you measure the transient phase, you get over 11 milliseconds. So here at a 90 hertz base frequency, we're now able to detect conductors that have time constants greater than 10 milliseconds. And the important thing about this, first of all, is this was only one flight line of 11 flight lines, and not all of the flight lines exhibit this high conductance. And normally in this environment, the higher conductance represents more sulfide. And so what do you want? You want to have the ability to drill the area of this target, which has the greatest likelihood of having the most sulfide, where the sulfide is known to be associated with copper, lead, and zinc. So to summarize, the transient phase method identifies high conductance targets based on the ratio of the total off time to the total on time. The method is waveform independent. It's not affected by the primary field during the transmitter on time, but it does break down for low conductance targets. And just one last comment. You can take any data set, any airborne data set. For example, Geotech has flown this survey in Northern Ontario. It's near Dubreuilville. It's in the public domain, and it's over 10,000 line kilometers. The data is fantastic. So you can export the calculated time constants for the for the B field and the dB by dt, and then you can sort them from low conductance to high conductance. And there's two things you'll find, and this is because we don't really know how to calculate time constants properly, is that there are very few high time constants. So you'll find that very few of these are higher than, say, 7 or 8 milliseconds. But more importantly, probably 90% of the high conductance estimates that are made in that data set are incorrect. Because of the way the time constants are calculated and what is actually happening in the Earth. So you can take a look at any of the systems. We all make the same mistakes, and we are doing a very poor job of estimating conductance. The transient phase is a simple method. It's very robust because you're taking all the samples. You're not just taking some of the late time samples, and it's independent of the primary field. Thank you. Right, so when I define a superconductor, it's a conductor where the conductance is not currently measurable with the system you are using. So in effect, it can have any conductance. But if you want me to put a number on that, let's say for a typical 30 hertz system, you can't really go much above, say, 10 milliseconds. So a superconductor would be 20, 30, 40, 50 milliseconds, and people typically are recording real-time constants using, say, borehole systems in the hundreds of milliseconds and into the second. So we're 2 orders of magnitude away from correctly estimating these. So we can't separate the conductivity or the thickness. We see that as a bulk parameter. So the conductivity times the thickness is only what we can measure.